This video shows a simple method to measure web modulus. It uses a long, full-width web sample that averages out variation across the width and along the length of the web. It requires only simple, inexpensive tools that can be done anytime and any place by two people. The test can be scaled up in size and tension depending on the web to be tested. Even if you have extensive tensile machine test data, I still recommend this test as it sometimes reveals web behavior that is not seen in tables of data. These are the tools we'll be using for the demo: a force gauge, a ruler, tape, scissors, a dowel rod tied with string, and of course, the web. Here we have the setup. We have the web taped down at one end, at the free end. We have the mark at 100 inches with a reference mark on a paper that we'll see how to use that in a minute. We have one loop around the dowel rod, not taped to the table. And the dowel rod with the force gauge attached that's been zeroed for pulling in a horizontal direction. The length and width of the sample used for the test depends on the modulus of the web. Since most of us can comfortably apply a tension of 25 newtons for an extended time, the width of the sample must be narrow enough that this slightly exceeds the stress, or force divided by width, that we expect to see online. The length of the sample must be such that 25 newtons of tension gives a 10 millimeter or 20 millimeter change in length of the sample. In any case, the length of the web needs to be at least 10 times the width to minimize end effects, and longer is always better for improved accuracy. I have seen samples 100 foot long taped to the warehouse floor. I've picked a narrower web since I have limited working length and width at home. You need a force gauge appropriate for the tension that will be required for the test. I'll use a 25 Newton spring gauge for this demo since the web is narrow and lower modulus, and 25 Newton should give all of the deformation I need for accurate measurement. I prefer a spring gauge versus an electronic gauge because they are less expensive, smaller, easier to carry around in your pocket, and they're easier to read when pulled by hand. However, electronic gauges work fine also. For this demo, I have a 5/8 inch wooden dowel slotted on the ends to accept the length of string. I have a loop in the string to accept the force gauge hook and keep the gauge centered on the dowel. First, we roll out about 10 foot of web and cut it. Next, we'll tape one end of the web to a work surface, and then we tape the other end to the dowel rod. We have to zero the force gauge so that it reads 0 when working at a horizontal position, and then we hook the gauge up to the loop in the dowel rod. Now, with the web perfectly flat but not tensioned, we mark the 100 inch mark on the paper that we're going to use, and we make sure that the paper is taped to the surface with the 100 inch mark in the appropriate spot. So here we are doing the pull test. Here we're pulling the sample in 5 Newton increments, pausing and holding at each increment to allow marking of the web. That's 5, 10, 15, 20, 25. Now we need to resist the urge to pull and break the web at this point. We're going to allow it to relax back to 0 tension, and we're going to look to see if there is any residual deformation after that pull. So as we do the pull test, we pull to each increment of force, 5 newtons in this case, calling out each force that we pull to. That way the person marking the paper, or if you have a scribe recording the data, they know what force you're pulling. So we've got our marks on the paper. We make sure that we've got the appropriate data so that we know which is the 100-inch mark and all the other marks at each tension. We've recorded our name, the date, the web, and any other pertinent information, including the width of the web that we've used in this sample. Once we have all the data, we can enter it into Excel in a table and let Excel do our calculations for us. So we have the length change, the strain, and the force that was applied to the web. We can plot this, making sure that we have the strain on the x-axis and the tension force on the y-axis. We can add a linear regression to the plot. Now we have to force this to go through 0, since modulus stress-strain plots always start at 0 tension, 0 strain. Without doing that, you can end up with an offset that's not captured in the modulus, and that can create calculation errors. So this is the test. It's simple, fast, and can be done anytime. It can be scaled up or down depending on the web. With the help of a second person, you can measure width as a function of tension. If you need more force or want to test wider webs, be creative. From this test, you can identify the linear elastic range of the material, or you can identify that it is a nonlinear, non-elastic material. You can do testing for permanent deformation. You can test for viscoelastic behavior. You can look for edge curl. And you can also check notch sensitivity. So there are a variety of things that you can do with this kind of a test that you simply cannot do in a tensile testing machine.